back. So I'm going to introduce Colleen Robichaux, who will be talking to us about positivity of Schubert coefficients.
Great, thank you all for having me today. So today I'm going to talk about some joint work with Igor Pak, in which we're investigating the computational complexity of particular invariants, for this case, the invariant of Schubert intersection numbers, which is sort of a departure from what a lot of you all are talking about today. But I think this line of inquiry is sort of capturing what some people might be interested in, because a lot of the, at least combinatorially minded folks here, might be interested in finding combinatorial rules to compute certain invariants, like Castelnuovo-Mumford regularities like we heard about yesterday, or projective dimensions, things like this. Finding some beautiful combinatorial formulas to capture these computations. And so sometimes these lines of inquiry are very hard, right? These are not easy formulas to actually get a hold of. And so a reasonable question to ask is, are these formulas that we are after always going to be possible? Or is there, in some cases, some obstructions that could keep us from ever obtaining the formulas that we want so badly? Okay. So today I'm going to talk about this question for Schubert intersection numbers, but you could do this for anything. So underlying everything in the talk, we're going to talk about computational complexity. So I just want to make sure we're all on the same page as to what these things are talking about. So at the bottom here, this is the sort of simplest class of problems, where the type of problems that we're going to talk about are called decision problems. And these are the problems that the answer to my question is either a simple yes or no. Okay, so is it sunny outside? Yes. So that is a decision problem. Okay, so for in this class P, so these are the classes that you can actually decide if the answer is yes or no in polynomial time. So this is as good as it gets. Okay, so some problems that you can do this for is, for example, two coloring of a graph. So I can decide if a graph is two colorable in polynomial time, because I can do a just sort of greedy algorithm walking along the graph to check if it is bipartite or two colorable. Another example is primality. So if my input is in its unary form, I only have to do a square root number of divisions to check that that number is prime. And so that tells me that primality is polynomial time. And what's even more incredible is, even if I restrict to an even more efficient sort of size of computation, doing everything in binary, it's also polynomial time, which is amazing. Okay, so that's P down here. If we go one level up, we hit the class NP. So this is non-deterministic polynomial time. Okay, and so these are the classes that, or these are the decision problems where you can check some evidence, some proof of yes in polynomial time. And so, for example, you could ask, is my graph 3 colorable? And you can check evidence that my graph is 3 colorable by you just giving me a 3 coloring. And I can check that it satisfies all of those conditions of being a 3 color. And so that's why 3 coloring is in NP. Another example is integer factorization. I can check if a given factorization is indeed a factorization of the number that I want you to factor or not. Okay, so these are in NP. Okay, now we can build up in this thing called the polynomial hierarchy, where we can build up level by level. By the level above, we say, these are the problems. For example, I can check a yes answer in polynomial time if I can cheat and look at the answers to any problem in the next class below in unit time. And so as we go up, we're getting harder and harder problems for this branch. And this branch, you might say, you didn't tell me anything about this. These are evidences of yes answer. This is evidences of no answer. Okay. And so we call these classes that are fitting in this framework, this is the polynomial hierarchy, or PH. Okay. So next, I want to study the complexity of some question to do with Schubert varieties, which popped up in the last talk. And so these Schubert varieties are living inside of this space called the complete flag variety. And this is the spaces where a point in the complete flag variety is a flag, which is a chain of subspaces from 0 all the way up to Cn, where at every point in this chain, I want to increase by dimension 1 at every step. And so we can identify the complete flag variety with just this quotient of GLN by the Borel subgroup, which this Borel subgroup is just our upper triangular matrices in GLN. And this Borel subgroup is going to act on our complete flag variety, and there are only going to be finitely many orbits with this action, and these orbits are going to be naturally indexed by permutations, W. And these orbits, I'll call these Schubert cells, and the Zariski closures of these Schubert cells are the Schubert varieties. Okay. So if you didn't like that construction, we also have a very explicit description of what these look like, just set theoretically. Okay, in terms of, I want them to intersect a particular fixed flag in certain dimensions that's controlled by the permutation W that's indexing it. So these are the sort of main building blocks that I want to study. And in particular, I'm interested in studying intersections of Schubert varieties. Okay, so one fact that's proven by Kleiman is if I intersect 3 Schubert varieties so that they're intersecting transversely, the intersection number is going to be the same. Okay. So if I choose G and G prime, some generic matrices in GLN, then whenever I intersect those translated Schubert varieties, I'm always going to get the same number CUVW. Okay, so it's some integer. It's counting some number of points in this intersection if I've chosen the dimensions of these Schubert varieties correctly, so that the answer isn't silly. Okay, so that the intersection is actually going to be points. And so in 1982, Lesko and Schutz and Berger identified Schubert polynomials as nice representatives for the cohomology classes of the Schubert varieties in the cohomology ring of the complete flag variety. And why would he do this? Well, you can use cohomology to give a rigorous framework for this intersection theory. And so by this 100 years of work giving this formalization, we found that we can actually compute these intersection numbers of these generic translates of Schubert varieties by just multiplying these polynomials called Schubert polynomials and expanding back into this basis of Schubert polynomials. Okay, so restating, if we're interested in computing these intersection numbers, all I have to do is multiply these polynomials and expand into this polynomial basis. Okay, so very concrete to actually compute what these things are. And the reason why this is so intriguing is not only is it just doing this computation on the level of polynomials, but these are very combinatorially interesting polynomials. Okay, so there'll be a basis of the polynomial ring. I know how to compute their monomial expansion in terms of explicit combinatorial objects. Well, we don't have time to get into all of the beautiful combinatorics of Schubert polynomials, but the list goes on. And so a natural question is, if we have this beautiful combinatorial structure, we know so much about these Schubert varieties so explicitly, and rich combinatorial structure there, these are some non-negative integers. And so can we come up with a manifestly positive combinatorial rule to actually compute them? So manifestly positive, I mean, I don't want any cancellations whenever I'm computing this rule. And combinatorial is a bit vague, but that's what many of us are looking for. We want some manifestly positive way combinatorially to compute these intersection numbers somehow. And this problem is proven extremely difficult. This is solved in some cases, but in general, this is rather open. And so let's cheat and ask a simpler question. And so I'll ask the question instead, maybe we can find a rule just to decide whenever this intersection is going to be empty or not. So how can I come up with a combinatorial rule to detect when these generic translates will meet in general? So I don't care how many points at which they meet, but do they meet at all? Okay, and so this number 2 is the question that we're going to dig into. But what is a rule? What we want to sort of formalize what a satisfying answer would actually look like in practice. And so today, I'm going to say that I want an NP rule to decide this positivity. So I want some condition that's in NP, so easy to give me some proof to check that this intersection is actually non-empty. Okay. You might want an extra combinatorial in there, But this will be our starting point. Any questions? Okay, so what do we even know about this Schubert positivity problem? I'll pick this up so that we can continue to see the question. Okay, so that's our main thing that we're looking for. And there are many partial characterizations of Schubert positivity. So there are very clearly stated ways that give some either necessary condition for the Schubert intersection to be non-empty, or some other sufficient conditions for the Schubert intersection to be non-empty. But none of these conditions actually, I can't patch them together to get a complete framework to detect when this intersection is actually not just going to be empty. Okay, and so, right, this has been a good 25 years of work. And so a natural question is it just impossible? Is it possible that no one there is no way to actually come up with one of these rules because there is a formal obstruction? Okay, so not that to say that people shouldn't look, but we should at least look to see if it's possible. Okay, and so people have been looking from a very combinatorial framework. And so whenever we're thinking about, let's just zoom out, because this is a problem with a rich algebraic structure. And so let's look at the very basic facts about the setup that we have and see if that illuminates anything for us. And so I'm going to zoom out to a very plain structure where I just have a system of polynomial equations in n variables. Okay, and I'll say I want it to be small. I want the coefficients to not be too big. I don't want to have too many terms in the polynomials, and I want to have too many polynomials in some sense. And so I can have this system of polynomials S, and you can ask, does this system have a complex solution, or a solution over C? Okay, so this is very easy to state. Okay, and I'll call this Hn, the question of asking, is this system satisfiable over C? Questions? Okay, so why is it called Hn? So this is named after the Hilbert-Nullstellensatz. Okay, so whenever we're thinking about what could possibly be some proof that the answer is yes, that this is actually satisfiable over C, the Nullstellensatz gives us a framework to detect when this should have a solution, because the weak Nullstellensatz says that my system is going to have a solution if and only if there are some other polynomials gi, so that they'll combine to give me the unit. Okay, so that's a very straightforward framework for the question. And so let's see what that gives us in terms of the complexity for this question. Okay, so in 26, Greta Hermann gives a doubly exponential bound for how big the degrees of these gi's are. And we can even get much more structure of what these GIs look like by the incredible work of the effective Nullstellensatz. So by all of these landmark results with the effective Nullstellensatz, we were able to whittle this down to say that, the degrees of the GIs are only going to be single exponential. So we know a lot about what these GIs look like due to all of this work. And so now, what does that tell us in terms of the complexity? Okay. So we can't just plug in a proposed solution because we don't know whatever complex valued solution is going to be small. So that's why we want these GIs. But the GIs could still be sort of big because even the best results tell me that these GIs are only single exponential. That's still sort of big. So I want you to think where this incredible breadth of work actually tells us where this is. Okay. With all of that, it's still not even in pH. So even with all of the incredible results of the effective Nullstellensatz, everything we know about Grosvenor basis theory, we only know that this is in P space. So we can actually figure this out. We can check evidence of yes if we're allowed to use polynomial amount of space in our computer, and we don't care about time. So we're sort of stuck. And so we either need some cleverness or something else. We need to be a bit more creative. And so we need cleverness. And then we'll also need $1 million hammer. So in this amazing work of Koiron, oh, I should just have 96 there. That's a typo on my part. But if we're allowed to assume GRH, we'll find that this problem is actually in the hierarchy. It's sitting within the second level. So if I'm allowed to use the generalized Riemann hypothesis, I know that this problem of deciding if the system of polynomial equations has a complex solution is sitting in the hierarchy, and it's pretty low, right? And just using GRH, this is an incredible improvement, right? I wasn't even in the hierarchy before, and now I'm all the way down here, which is absolutely incredible.
I already forgot what GRH stands for.
The generalized Riemann hypothesis. Yeah, thank you for that. Right. So I would like to rework the Schubert intersection problem so that I can actually appeal to this incredible result. But everyone likes to toss this generic condition around, but it can really muck things up, okay? Because my Schubert intersections, I can formulate them rather explicitly in terms of equations, but I have to make sure that whatever translations I use are actually generic, and that's hard to actually test. Okay, to test genericity in this case, I need to be able to test that my intersection is actually zero-dimensional and that there is no multiplicity in the points, if I'm actually wanting to capture everything that genericity wants. Okay, so that's absolutely non-trivial. And so it's not clear that you can actually simulate this genericity in this HN framework. But we do. And so we show that actually this problem of deciding if the Schubert intersection number is empty or not is in NP. You can actually get some polynomial time check with some certificate that there is actually a flag in this Schubert intersection generically. But we need not only $1 million hammer, but $2 million hammers. So we need GRH again, and we need this thing called strong de-randomization, which tells us that these classes are actually the same. So this is widely believed to be true, but this is a substantial strengthening of P does not equal NP. So this is a strengthening of P equals NP. This is a strengthening of B equals PPP. And then we're all the way out here. Okay, so this is a weighty assumption, but it is an assumption that many believe to be true. And so with these two assumptions, what we can do is appeal to a small formulation of this system. So Heinz-Satilli in 2018 gave a beautiful system for cutting out these Schubert intersections that it's not necessarily obvious that such a small system should even exist. Okay, if you look at the classical definitions of the Schubert varieties, you might think that you have to use some determinants to cut out membership in a Schubert variety. But Heinz-Satilli show you, no, you just need bilinear equations. You need a quadratic number of bilinear equations, and you can actually cut out membership in the Schubert variety. So that was amazing. And to simulate this genericity, we use a parameterized version of this Hilbert-Nussbaum-Zatz decision problem that was studied by Ait El-Mansour, Balaji, Nosenshir, Mohadami, and Worrell just last summer. Okay, so using this parameterized version, we can simulate these generic intersections well enough. And then assuming that NP is equal to AM and the GRH, then we get our result. Okay. And the last thing I'll say is we, in this framework, we're working in Schubert varieties that are built from the complete flag variety, which is type A case. But you can do this for other flag varieties, other generalized flag varieties. So we call these different types. And so we get results for types A, B, and C. And with David Spire, we get type D. Thanks.